The title of this presentation is PDE Models of Biological Transport. To give a presentation overview, we'll be discussing different approaches that are dependent on transport and biology. And from this, we'll want to introduce two references on the literatures from PDEs associated with these types of processes and closely related ones. And we'll want to introduce a reference from the quantum physics literature, in particular quantum algorithms for solving PDEs and systems of PDEs, and how we can make use of and apply this methodology in a completely different circumstance for forming different physically oriented interpretations. And we'll present a few simulation results obtained from the algorithm. So first, what we want to realize is that biological transport occurs under many different types of circumstances. We can look for different ways in which either diffusion can occur depending upon the direction in which passive transport occurs, which can also be related to the fact that there's some release of ATP along an active transport mechanism that's given in the first reference for a picture. From another reference, we can also see that within the extracellular space, and there can be a barrier from the cell membrane that's separating the extracellular space and the intracellular space. And from these different types of protein channels, it's possible for molecules or carrier proteins to undergo some type of directed transport in which they can pass from the inside to the outside of the cell membrane through these intermediate passages and these intermediate mechanisms which lie in between or are interspersed in between the cell membrane. And then we can also see in the final image that's given in the bottom of the slide that there can also exist a similar orientation or a similar mechanisms, either involving carbohydrates and these pores, which we had described in the second image, which can separate the extracellular fluid from the cytoplasm, and this can mediate and determine which types of proteins or also can pass through the pore to beyond the channel protein to enter this cytoplasm, as well as whether cholesterol or other glycoproteins can also be situated within the cellular membrane. But there can be some type of ambiguity and difference in which one describes biological transport, in particular the scale on which this type of transport occurs, because it can occur in other larger scale environments rather than just within the cell that we were giving examples of and motivating in the previous slide. In particular, this reference from 2019 shows how there can exist a different type of transport that is given from materials that are found deep within the ocean, in which, depending upon the density and whether the boat, which is this crane, is pulling up the material through different layers of the ocean, there can exist different influences of biological material as this material is being transported throughout different environments and the organisms that interact in these environments. So to make use of the fact that we can think of making use or implementing partial differential equations as interesting or accurate models of biological transport, there's a reference from the literature which is occupying this space between biology and trying to look at how algorithms or different types of models involving partial differential equations can be used to model these phenomena. And this is one of the such partial differential equations in which, when we mean a partial differential equation, we're looking at the existence of some smooth solution which depends in time. And in this case, from an older reference in around the 80s, they provide a closed form for one such partial differential equation, which can describe diffusion and transport phenomena that we've been mentioning different examples of. And it's given by this expression here, in which the solution P is dependent on time, and then the other side of the partial differential equation is completely dependent upon either some scalar parameters which are given by alpha and beta, P over Q, where P is the solution again, with the exception that we're not differentiating it in any of the places in which P occurs, as well as a second spatial derivative of the solution with respect to x multiplied by some diffusion constant script d. So the first term in the partial differential equation with the diffusion constant really mediates and communicates to us what is the strength of this diffusion process with respect to other competing terms that are given in the partial differential equation. And then there can also exist several other different types of formulations for this type of diffusion partial differential equation that was given in the previous slide, in which another reference from the literature very much provides a perspective that has gained a lot of interest recently, in which one can make use of neural operators or other related computational methods for trying to learn solutions of partial differential equations from different training data sets. And this is very much taking a similar, taking the same type of approach that these methods do with neural operators and related methods. And in particular, for their data generation step, they provide three different ways, three different versions of a diffusion advection equation, which is given here by 2.1, 2.2, and 2.3. And the difference is that these diffusion advection equations, they're very similar to the statement of the partial differential equation that was given in the previous slide, because it involves a constant big D in front of the second derivative of the solution, which is common to the PDE in the previous slide. But there are also different competing nonlinearities that can be dependent upon real constant CRR. So that's a different way to really make use of or build or construct similar types of partial differential equations, which share in the original statement of the 1980 or 1979 PDE from the previous slide, because they have the same dominant nonlinearity as the first term from the second derivative of the solution, and then they have lower order terms, which can constitute the order of different nonlinearities or processes throughout this diffusion process. And now we're going to actually introduce and make use of a variational quantum algorithm that's in the literature from these authors. And it's a really interesting paper that's continued to get attraction, a lot of attraction and attention recently, in which the main points of investigation that we were interested in a group that I used to be a part of, in which we would like to think about and determine whether quantum algorithms can solve well-posed initial value problems, and also whether the solution approximations generated from such algorithms compare to classically computed solutions that we already know. So it's really trying to determine whether a different class of algorithms that don't have to be classically implemented can still at least have some type of quadratic speed up, which is modest, and in the best case, whether there will be some type of exponential speed up in the runtime of this algorithm that can help us solve these systems of partial differential equations for diffusion advection that we've been discussing. And this is to say that I've talked about this type of algorithm in different instances that are given by some other videos on the channel. And it's also more detail on this algorithm, how it's implemented for 15 partial differential equations, is also provided in this preprint that's been up since the latest version since November of last year. And we can make use of the PDE solver for our quantum algorithm to solve these transport problems, in which we can see that we would like to determine whether the variational quantum algorithm can solve a PDE's concerning the diffusion advection equations in the three forms that are given on the slide. The first is the 1979 reference of the PDE, and the two other ones are from the second reference for learning partial differential equations that are given as different types of versions of the diffusion advection partial differential equation. And the first step that we have to go is that for the variational quantum algorithm is that we can form a cost function from the PDE, in which it involves some type of discretization and expressing a cost function in terms of a superposition of variational parameters and expectation values, which we can write. It's a complicated expression, but we can obtain it. And then we can see that from our formulation of the cost function, there are different sections involving, as we had mentioned previously, the variational parameters different in different Brockett states. And it's important when we're running this algorithm to make sure that we appropriately position the quantum algorithm when we're beginning our simulation so that we can obtain a good coverage of the Hilbert space. And from this reference from February of 2022, these authors describe uh, different aspects of Ansatz expressibility, in which they're looking at different ways to express the initial state that a variational quantum algorithm would time evolve to obtain additional solution approximations as we continue propagating time forwards. And we can look to directly implement this algorithm under different choices of initial conditions for the PDE, which in our quantum algorithm language, it just means that we're looking at different initial states that the quantum algorithm time evolves, and we can run it with different starting initial configurations, and we can see that if we use the Nevergrad optimizer, which I've discussed in my other videos, but it's a really great open source optimizer provided by Facebook, we can interface this optimizer with our quantum pipeline to serve as so that the Nevergrad optimizer serves as the optimization step, which helps the quantum classical feedback loop continue for potentially hundreds of thousands of time steps, depending upon how long someone wants to run the quantum algorithm for. And we can see that for different time steps, there can exist different types of behaviors and oscillations to the solutions, in which in some cases of biological transport, physically, we can expect or maybe anticipate that some of the motion that the particles surrounding the cell or in other environments of the body, it can undergo some type of periodic motion in which the velocity or the amplitude of the velocity of the body within the extracellular fluid or the cytoplasm or near the surface of the cell membrane could either decrease or increase or oscillate rapidly, as we've shown with these two sinusoidal solutions. And we can see that for other initial starting configurations, we can continue to slightly vary the initial state that we give for the partial differential equation, which would be the trajectory of biological transport. And then as we time evolve for 500 time steps, which we were just doing to see how the algorithm would fare or how it would perform, we can see that there can just be other similar ways in which the periods of motion of two trajectories of biological transport can differ depending upon the time step magnitude that we take, as well as the initial condition, which is influenced by the optimizer that we mentioned we were using from open source from Facebook. And for the remaining PDEs of describing transport, there can be several other nonlinearities that are common to those described by the Kamasa-Holm PDE. This PDE is a really interesting one, and it's probably the one that was most involved in a lot of the simulations that were ran from the archive preprint that I mentioned from November of last year, in which to form the cause function, you have to isolate for the time of a variational state from the time derivative of the solution of the PDE, and there exists many nonlinearities, including third order partial derivatives, second order partial derivatives, first order partial derivatives, and so on, in even these terms. And one can also express the Kamasa-Holm equation in terms of a PDE system, which is given from this form. And this is just to say that many of the nonlinearities that were studied and classified and experimented with in the Kamasa-Holm equation, they share in the nonlinearities that are present in the diffusion diffection equations. So even though the statement of both of these partial differential equations isn't exactly the same, running the algorithm in different types of circumstances can still be done, and it can allow us to compare different nonlinearities of other partial differential equations depending on the initial condition that we use. So even though they're not exactly the same, many of the similar behavior of the nonlinearities is apparent and is present in this PDE for the remaining biological transport PDEs. And the more information on all of the simulations and the cost function for the Kamasa-Holm PD is in that archive reference. So I wanted to close out with some conclusions in which we introduced biological transport and several circumstances under such which transport can occur. And we stated different types of PDEs which can be used to model such phenomena. And we motivated how the quantum algorithm can produce similar approximations to solutions of such PDEs after passing initial data for the solution from what's already obtained from classical algorithms, and how we can also make use of other simulation results and methods from the quantum algorithm to think about what would the classical algorithm's performance be if it would still always be better. And we established similarities between the Kamasa home PD and other transport equations. And thanks for watching.